So today we're continuing the 2013 USNCO local exam walkthrough series, and we've got questions 21 through 30 lined up. So starting with 21, it's a pretty simple question. They basically just want the standard enthalpy change. And you're given heats of formation for all relevant compounds. This isn't considered relevant because it's an element found in its standard state. Like that's how you'd find it in nature, because it's just, basically you can just take it as automatically diatomic. So basically, the heat of formation of Cl2 would be 0, just like it would be for O2, N2, H2, things like that. So, using Hess's law, you can find the overall change in enthalpy by just doing products minus reactants. So, this is essentially our setup. So, those are the products, that's the minus, and we only have to consider methane. And that comes out to this value. If you apply sig figs, then A. 22. We're combusting 10 grams of ethanol, and we're given the amount of heats that's released. That's a lot of heat. Okay, and we're basically asked to find the molar enthalpy of combustion. What this means is basically, at standard conditions, how much heat will 1 full mole of ethanol release? The reason it's not this much is because we weren't using 1 mole, because the molar mass of ethanol is 46,068. So that means we were only using 0.217 moles of ethanol. Obviously, if you burn more stuff, it's going to release more heat. So if we do 296.6 kilojoules divided by 0.217 moles, that will show us that we're actually going to release a lot more heat if we burn 1 mole of ethanol. Alright, moving on to 23. Positive change in enthalpy. Entropy, my bad. There's, I think, usually 1 or 2 questions every year on the local exam on this topic. Basically, what you're looking for is a difference in states of matter. If you go from a solid to a gas, that's a really positive change in entropy, because a solid's all locked in, molecules can't move around very much, they can only vibrate where they're at, whereas a gas is pretty much free to go wherever it pleases, and it's got a much higher average velocity, so it's packing a lot more disorder, more entropy. So using that idea, we can look at our choices. We have 1 mole of gas, so 1 mole of O2, compared to 0 moles of gas. So essentially, this is a negative change in entropy, so A is not a good thing to choose. We have 7 moles of gas compared to 4 moles of gas and 2 moles of a liquid. Once again, we're decreasing moles of gas, that's not the way we want to go. Here we have 0 to 3 moles of gas. That's pretty encouraging because it's a large positive change in the moles of gas, which basically correlates with entropy change. Here we go from 3 to 2. Once again, that's a decrease, so we would not choose that. Which statement is incorrect? Okay, so for 24, let's look at this equation. I don't think it has a name. So basically, changing Gibbs free energy at a certain temperature is equal to the change in enthalpy at that same temperature minus T times the change in entropy at that same temperature. So here's the rundown. You want delta G to be negative for your reaction to be spontaneous. That's just how spontaneity is defined. So in order for this to be negative, you could have a situation where delta H is negative, and here I'll make 2 columns. I'll get rid of that dot 2. And you could have a situation where delta S is positive at the same time, because you're multiplying by negative T, essentially. So a negative plus a negative is going to get you, without doubt, a negative. So any reaction described by these two things, a negative change in enthalpy and a positive change in entropy, has to be spontaneous. But here, we've got a positive change in enthalpy. So let's explore that situation, or those two situations, because we could have two different things. Say we have positive entropy change. We could still be negative. It's just that negative Ts has to have a greater magnitude than delta H, because you have to, like, if we call this A minus B, B has to be greater than A if you want to end up with a negative number. So plus plus can still result in a negative delta G, but the temperature just has to be really high so that the magnitude of B can increase, and essentially you're just subtracting the same quantity of enthalpy change by a larger T times delta S. So this is an option. But if we look at this, plus minus, there is no way we're going to get a negative number from a positive number adding a positive number, because the minuses cancel out. Like, you can't add positive number, expect to get a negative number. So this will never be spontaneous. So let's look. This reaction is spontaneous at all temperatures. No, we covered that only the minus plus situation is spontaneous in every condition. Spontaneous at low temperatures? No, because if the temperature is low, remember we're talking about the Kelvin scale, so temperature can't be negative. So low just means positive but close to zero. That means the quantity T delta S has a lower magnitude, so you're not subtracting by a huge number. And if you're not subtracting by a huge number, there's a really good probability that delta G is going to be positive. So that's not our answer. Not spontaneous at any temperature. We covered that that was a plus minus situation, so our answer has to be B. Okay, looking at 25. Alright, we don't even care about this rate law. Basically, we know that A is disappearing at this rate, and because we have this reaction, we know what ratio that they're reacting in. So it's a 3:2 ratio. So if A is disappearing at a rate of 2, B's got to be disappearing at a rate of 3. That's as simple as it gets. You don't have to look at the rate law for this, or for these types of questions, where it's just talking about rate of disappearance, rate of appearance. What are the units for the rate constant of a second order reaction? Okay, so let's think about this. Let's just draw out the equation for a typical second order reaction. You could do a squared or ab, it doesn't matter because units are going to be the same. Rate is measured in molarity per second, which will be moles per liter seconds, equals, we'll leave the spot for K blank for now, and then molarity squared. So if we divide by molarity squared in order to get K by itself, we have this, get rid of the 2, get rid of the top, so 1 over, and this will be our units, and that corresponds with B. Alright, for 27, the counts of a Geiger counter, basically what it's corresponding to is how much, okay, I'm going to explain this really crudely, but how much radioactive stuff that has not decayed yet. Basically, what you have left to react. So if you have 2000 to begin with, and you have 250 later, well, obviously you're dividing by 8, but it's the same thing as 2 to the third, so that means you've gone through 3 half-lives. Because, once again, I'm just going to reiterate that the counts per minute directly correlates with how much stuff that has not decayed. So you went through 3 half-lives after 120 hours, and radioactive decay is first order, meaning that your half-life isn't going to change over time. It's going to be constant, and basically you just do 120 over 3 equals 40. 28, rate limiting approximation. Okay, so basically you probably learned this in your Chem or AP Chem or IB Chem class. Yeah, you would just answer slowest. But the logic behind that is if you have a two-step reaction, say the first step is the slowest, the second step can't proceed until the first step produces enough of that product, right? Because the second step doesn't have anything to go off on. It has to have a sufficient concentration of its reactants. Some of its reactants must be the first step's products. So until the first step goes forward sufficiently, the second step can't do anything. So that's why the first step determines the rate. And if you flip it, if the first step is fast but the second step is slow, it's pretty much the same thing. The first step, you can just consider it said and done. But until the second step is actually done producing what it needs to, your reaction is not complete. So the rate depends on the slow step. 29. This is basically just vocabulary. Homogeneous and heterogeneous. In the context of catalysts, is talking about state of matter. So homogeneous would mean, like, for example, you have a gaseous catalyst in a gaseous mixture of reactants. So your reactants and catalysts are in the same phase, and heterogeneous would be like a solid catalyst in an aqueous solution, mixture of reactants. So let's analyze our choices. We have a solid and gases, that's heterogeneous. We have a gas and a gas, that's homogeneous. We have aqueous and aqueous, that's homogeneous. Number 30. What's the activation energy for the reverse reaction? Okay, so the activation energy is basically the hump you need to get over in order to get the ball rolling for your reaction. In crude terms. It's also easier to explain it like that when we're looking at this reaction progress energy profile. So let's consider that we're going in this direction because we are going from products to reactants. The hump that we need to go over starts from 60 and gets to about 85. And then after here, it's just downhill. That's easy for us. Like if we're considering that we're riding a roller coaster, right? Once we get to the top, gravity can do its thing. We just need to provide the energy to get there. So basically 85 minus 60 equals 25. Alright, that's it for this video. Stay tuned for the next one.